the new year. I don't feel any different.
Now that we've stated this big theorem and introduced the ring of fractions and field of fractions, in this video, I want to give some examples. Later, we'll come back and prove that theorem that we stated. So let's start with the simplest example is the one that began this lecture. Take the ring to be Z, that's an integral domain. So we can take D to be all the non-zero elements of Z. And the field of fractions, this ring that contains an isomorphic copy of Z in which all the elements of D, the non-zero elements of Z, become units. Well, what is that? It's equivalence classes of pairs of elements in Z up to this equivalence relation that we saw at the beginning of the lecture, and we exactly get Q. So maybe a more interesting example is if we take the ring to be 2Z, the field of fractions is still going to be Q. So this is still an integral domain. We can take D to be all the non-zero elements of 2Z. And okay, part of the theorem is the elements of the field of fractions of this ring of fractions, and in this case, it'll be a field, is R are things of the form R times D inverse, where R is in 2Z, D is in 2Z non-zero elements. So in particular, what are we going to have? We're going to have things like the equivalence class of 2 over 2k for any k that's not 0. Also, we have 2k over k for any k that's not, sorry, 2k over 2. Sorry, I'm going to be more careful here for any k. So even though 2z doesn't have an identity, if you take k equals 1, you get the class of 2 over 2, and that is an identity in this field of fractions. So there's no identity in this ring, but when you go up to the field of fractions, an identity appears. So another good example to think about, very much like the relationship between Z and Q, is if you take D to be a square-free integer, you can take the quadratic field Q adjoins square root of D that was introduced in section 7.1 that we talked a lot about in 206A. Inside that field, there's this quadratic integer ring O cubed square root of D, which is this ring that depends on whether D is 1 mod 4 or 2 or 3 mod 4. These rings are going to be really key examples for a lot of the things that we'll talk about in the first part of this course. So I recommend you review the stuff that we talked about with them. But if you start with this quadratic integer ring and you ask what is its field of fractions, you exactly get Q adjoins square root of D. And you'll be able to see why that's true if you think about what is the inverse of an element in Q adjoins square root of D. How do you write it? How do you write the inverse of an element? So this is a good thing to check. All right, so the next example is going to be a little longer discussion. Let's say that R is an integral domain. We have seen that that means the polynomial ring R bracket X is also an integral domain. What is the field of fractions of R bracket X? So this is this integral domain. We can take our subset D to be all the non-zero elements of R bracket X. Well, that gets a special name. That's called the field of rational functions in X over R. And I'll pause and erase, and then I'll talk about what the elements in this ring look like. Let's continue this discussion of the case where R is an integral domain, so R bracket X is an integral domain as well. We want to understand the field of rational functions in X over R, which is the field of fractions of R bracket X. So what do its elements look like? They're quotients of polynomials, or really equivalence classes of ordered pairs P of X comma Q of X up to this equivalence relation that's going to come from cross multiplying. So P of X over Q of X are both in R bracket X. Q of X is not 0. P of X and Q of X might be constant polynomials, though. Right? You could just take them to have degree 0. So these could be elements of R. So you can see that this field of fractions of R bracket X is going to contain the field of fractions of R as this equivalence classes where both p of x and q of x are constant polynomials. Things that look like a over b, where b is a non-zero and a and b are any elements of R. So let's call this field of fractions of R, let's call that F. And the field of rational functions in X over F is denoted F parentheses X. So here we're talking about the field of rational functions in X over R. So if we take our ring R to be F, the field of fractions of R, this gets a special notation, F adjoin X or F parentheses X. So let's talk about the specific case where R is equal to Z, and that'll help make it clear what's going on in general with the relationship between R and F. So if you take R equals Z, we know the field of fractions is Q. So what does this field of rational functions in X over Q look like? Well, it has elements that are quotients of polynomials. P of X over Q of X, where P of X and Q of X are elements in Q bracket X. They have rational coefficients now. And Q of X can't be 0. And the key observation is that you have these two polynomials that have rational coefficients. So maybe they have denominators, but you can multiply by some integer to clear all of those denominators. So there exists a non-zero integer n, where you multiply p of x by n and q of x by n, and you get two polynomials that have integer coefficients now, instead of just rational coefficients. And the key observation is that with this equivalence relation, n times p of x over n times q of x is the same element as p of x over q of x. So you cross multiply and you get the same thing. So these are going to be the same in this field of fractions. So what does that mean? Anytime you have a ratio of two polynomials that are in Q bracket X, you can replace them with two polynomials in Z bracket X and get the same equivalence class. So what we're seeing is that the field of fractions of Q bracket X is the same as the field of fractions of Z bracket X. That taking ratios of polynomials whose coefficients are rational, you don't pick up anything extra that you don't already get by taking ratios of polynomials whose coefficients are integers. And the key idea is you can always multiply by some integer to turn these rational coefficients into integer coefficients. And okay, you should think about the details, but the same statement is true in general. If R is an integral domain and F is its field of fractions, the field of fractions of R bracket X, this field of rational functions in X over R, is the same as the field of fractions, the field of rational functions in X over F, this F of X, the field of fractions of F bracket X. So if you want to understand the field of fractions of a polynomial ring, R bracket X, where R is an integral domain, then all you really have to think about is first take the field of fractions of R and then take the field of fractions of the polynomial ring, where instead of taking coefficients in R, you take coefficients in F. It doesn't make a difference if you take the coefficients to be in the integral domain or in the field of fractions of that integral domain. Okay, so in the next video, we'll prove this big theorem and make all of this a little bit more precise by talking about what exactly are the elements in this ring Q that is guaranteed by the statement of this theorem.